Okay, thank you, Chairman. I want to talk about aluminum-based coating for preventing hydrogen ingress in high-pressure systems. My name is Hiroshi Nishiguchi from National Institute of Technology, Sasaki College, so-called COSEM in Japan. The background, this slide shows the hydrogen station operating status in Japan. While there are 30,000 gas stations in Japan, only 157 hydrogen stations are operating now. So it indicates a slow propagation towards hydrogen society and carbon neutral society. This reason comes from hydrogen embrittlement, which is that hydrogen affects the strength property of materials. This slide shows the previous report of our research about fatigue crack growth that was presented in 5th International Conference Crack Class. So this picture shows cracks from artificial hole, 0.5 millimeter diameter. Okay, this is the uncharged one. This is in the presence of hydrogen. In the presence of hydrogen, the number of cycles of fatigue cycles is even it's same, but crack propagate longer than that of uncharged one and sharply propagate. This is from this picture we can see hydrogen affect crack propagation. Then this graph shows the relationship between hydrogen content and fatigue crack growth acceleration with by the hydrogen. Okay, the fatigue crack growth acceleration will be increased with the increase in hydrogen content like this. But I thought that graph would be like this, but there are upper limit. If the hydrogen content is too much, the upper limit 30 times. Okay, this graph explains to us, don't worry about hydrogen embrittlement too much. Okay, this result can be the guideline of design for carbon steel using. But anyway, we must prevent hydrogen embrittlement. So we are researching about coating to prevent hydrogen ingress into materials like this, the pipe with coating. Okay, there are several coating methods, but I want to focus on powder heat treatment coating formation method. This is the aluminum powder and base metal are packed in the furnace and subject to high temperature, then coated material can be obtained. Okay, so I want to talk about hydrogen ingress prevention, strength characteristics, simulation of hydrogen ingress prevention in actual components. I want to talk about it. Experimental method. These are the materials used in this study: anneal to carbon steel S25C, 45C, low alloy steel SCM, and austenitic stainless steel SUS 304, and cast iron. So shape and dimension of the specimen for hydrogen measurement like this. This is before coating, and these are the coated specimen. I prepared two types of low aluminum content and high aluminum content specimen. Okay, this is a condition of hydrogen precharging. The specimens were exposed to 100 megapascal high pressure hydrogen gas and 85 degrees Celsius. This is a maximum temperature of used in hydrogen station and 1 day. Hydrogen content was measured by gas chromatography type thermal desorption analyzer TEA. There are two types of specimen. At first, coated specimen removed a coated part, a hydrogen precharging, and hydrogen measurement. Second, coated specimen, hydrogen precharging and remove the coating part, TDA. So if I compare these materials, we can know the coating effect against hydrogen ingress. So I calculate hydrogen cut ratio by this formula. Okay. Now, this is I also conducted tensile test of coated specimen. The material is carbon steel S25C steel, and shape and dimension like this, and cross speed is 10 millimeter per minute. During tensile test, I stopped the tensile test and I take a replica at the lateral surface in order to observe the crack initiation at the lateral surface. And I observed the fracture surface and using SEM. Okay, this is the SEM image of microscopic cross-section before tensile test. Okay, these are the S25C steel, very parallel carbon steel. They are coated parts, both low aluminum and high aluminum. Okay, these in other materials, they are also coating parts. Okay, next. This slide shows the EDS line profiles of microscopic cross sections. Okay, as far as S25C, aluminum content is decreasing with the depth, and in contrast, Fe content is increasing. Okay, this is a low aluminum case. In contrast, high aluminum case, and aluminum and Fe content keep constant at the coated part, and these are base metal. Okay, the coated thickness is approximately 50 micrometer, and same tendency are seen in other materials. Okay, this left side graph shows the thickness of various materials. There is no significant difference between low aluminum and high aluminum content materials. Right side shows the biggest hardness. There is no significant difference in all materials. However, high aluminum materials are approximately twice as hard as low aluminum materials in every materials. Okay, experimental result. This graph shows the TDA hydrogen release profiles about SUS 304 steel, austenitic stainless steel, and low aluminum and high aluminum. This graph shows the without coating and with coating. Okay, I want to explain briefly about the graph. This area surrounded by graph and the horizontal axis, this area is corresponding to the hydrogen content in the base metal. Okay, as you can see, the peak is decreased to the zero. Then this suggests that coating prevents the hydrogen ingress into the base metal. Also, this is a cast iron, low aluminum, high aluminum. The peak significantly decreased, but not zero. Left, a little left. So, but this is a very good coating. So this is the difference of the rate of hydrogen cut RHC in various materials, but mostly the RHC shows the 100%, except for cast iron. Then coating effect exhibited mostly complete in every case of the base material. Now, this is the result of tensile test of coated specimen of carbon and steel. Okay, this is a load and cross-head displacement with lateral surface morphologies. In elastic region, there are no cracks, but cracks initiated after the onset of plastic deformation small number, but large number initiated and propagated. These are the tensile strengths of base metal, reduction area, residual hydrogen content are the same. In both cases, uncharged and highly precharged one. And fracture morphology shows both kappa and cone fracture. This is a SEM image of lateral surface of ruptured tensile specimen. These are the uncharged one, hydrogen precharged one. So there, you can see there are many cracks at the lateral surface. However, there was no clear difference between uncharged and hydrogen precharged. For example, the number of cracks, the length of cracks, there are no difference. Next, these are the higher magnified picture, uncharged and hydrogen charged. This red circle shows maybe you can't easily see, but they are initiated tiny, very small cracks inside of the red circle, are relatively narrow space in uncharged one. In contrast, in case of hydrogen precharged one, relatively widely distributed tiny cracks. But there were a little difference in distribution of cracks. But it didn't affect on the macroscopic fracture morphology. Okay, this is the macroscopic morphology of ruptured tensile test specimen. This is a kappa cone fracture. There are coating part and interface and base metal. Okay, many surface cracks initiated from the coating parts. Okay, and propagate into the base metal. However, these cracks branched like this, branched and stop propagation. So then, kappa and cone type fracture morphology is not changed in uncharged one, hydrogen precharged one, and coated one or uncoated one. Every specimen has kappa and cone type fracture, which indicate fracture was initiated from the void coalescence from the inside of the specimen, not the crack as a coated part. Okay. Then this is the XRD analysis of coating part. This is the S445C carbon steel. Blue line shows the low aluminum, and red shows a high aluminum content. In case of low aluminum content material, FEAL only checked by XRD analysis. But however, in contrast, high aluminum content material, there are many kinds of FEAL alloys. So also, austenitic stainless steel has shown, but the number of alloy types is fewer compared to S45C steel. Anyway, in high aluminum materials, different alloys are mixed. Previous reports from Professor Yamabe, the aluminum hot dipping coating method resulted in hydrogen being trapped as the interface between aluminum and FEAL alloy interface. Hydrogen was trapped and preventing hydrogen ingress. So from this paper, it is believed that hydrogen is stopped by the mixed interfaces, resulting in a hydrogen ingress prevention effect. But we want to do further investigation about it. Okay, next, the analysis of hydrogen diffusion into the steel. This is the joint models without coating and with coating. Okay, the presence of coating and the absence of the coating result in a significant difference in hydrogen diffusion, quite low. And this is the other type of joint, I think, without coating. There are about 30 times hydrogen diffusion is very late. Okay, time has come, so I will have a conclusion. The time has come, so I will skip the conclusion. Thank you so much.